Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for anything I want to talk about science and math. And today we are doing the notes for AP Chemistry Unit 5 Kinetics. This is the wrong screen. Got to get to the right screen. And I need to actually close this out so that I can write on it again and reopen it. Leave. I'll erase it. Come down here. Come down here. Desktop. AP Chem. Come on. Might not let me do it here. Oh, it's doing it. Unit 5. Notes to write. Ta-da! Okay. That erased it. Now let's see if I can scroll back to the top. All right. So this is what we're learning, kinetics. Like I told the class before the video people joined us, it's considered a hard part, but it's not really hard. It's reputation. It's just easy stuff that sounds fancy. Okay, so reaction rate. So kinetics, the term is about how fast a reaction happens. Draw, we'll put red, fast. So we learned a tiny bit about this in honors, but I liked it. I was looking at your book. Your book is chapter 14, the Pearson chemistry book. And it talked about the Arctic squirrel, that they hibernate like half their life. And how they're able to do that is when it's cold, its metabolism reaction rate slow down and it conserves energy. And it can just sleep half its life. And it's so cute with its little ears. You should look at it in your book or online. But it's very cute. Little hibernating squirrel. Okay, so how do reactions occur? And this is what Ella had said earlier. With collisions, they have to collide. Collision theory, the atoms have to collide to react. Now, this is straight from honors. Things that affect a chemical reaction. Sometimes they're called stressors. So the first one is you can increase the temperature. You can add heat. And this increases the atom's speed so they collide faster with more force and more likely to react. Also, the activation energy may be supplied. Now, we're going to talk more about that later in these notes. Another thing you can do is you can increase the concentration. Y'all remember this from honors? More particles, more chance of collision. If it's a gas, you can increase the pressure. Big P is pressure in chemistry, so I'm going to just leave that there. I'm not going to write out pressure. Okay. You squish them together, there's more chances of collision. So also the state of matter kind of goes in this too. Like a liquid might react better than a gas because the particles are closer. A homogeneous solution will react better than hetero. If they're in different layers, they won't mix, they won't react, and they won't have as many reactions. So that's all something. I think your book talked about that. I read a bunch of different sources because y'all know I've been changing these notes, seeing who included what. Another thing is the effects of the surface area. Smaller particles have a greater surface area to volume ratio and react faster. And my example for this is always exploding grain silos. So when I was in grad school at Georgia State, I was getting a degree in physical therapy. I was taking a chemistry class, and my professor was from out west. And out west, where they grow grain, they have problems with grain explosions. And we don't ever worry about that. You're eating corn on the cob for Thanksgiving, you never worry about blowing your head off. But my professor had lost 2 friends who had died as teenagers in grain explosions. And if you look at, if you Google it or whatever, you can see that they have, where the farmers take the grain to be processed, there's these giant signs as big as that wall that say, stop, no smoking beyond this point. If your car backfires, do not enter these gates. Because what happens is where they bring the grain in to process it, it ends up being dust. It gets tiny little pieces of it as it's flowing, and then that dust has so much surface area it becomes explosive, and any little any little spark will blow up. And it's like, this is something we would never think about here. It's very humid. where the air out there is much more dry, but it's all about that surface area. So he got a little sad about it, about his friends dying, even all these years later. Another thing is the chemical nature. Substances vary greatly in their ability to react. Another thing that affects the rate is by adding a catalyst. Y'all learned about those in biology, and we'll talk more about them in this unit. But a catalyst speeds up a reaction without being consumed. And the one you learned about in honors biology was proteins in our body are called enzymes. And often catalysts work by lowering the energy of activation. Sometimes they're like matchmakers putting chemicals together. And we're going to talk about that more, learning target number 11 here. So the next thing for this part of the test, one of the things they'll do is they will put this graph, and I know y'all's didn't run off good, so you're going to need to darken it. This line is products. This line is reactants. Kevin, are you paying attention? I don't think so. I think you have a phone in your lap. Put it away and focus. This is not hard if you will just pay attention. Okay. What?
I was tying some.
You were what?
I was tying my string.
You were tying your string. Okay. That's fine. But don't even pay too much attention to your string. Okay, so products, so this is extremely logical. So it's like something that is unnecessary to make as a graph. But remember, for AP Chem, they're trying to trick you. And they try to make easy things look more complicated. And one of the ways they do it is by making graphs. Because in general, people don't like graphs. It's like how people don't like fractions. But this graph is so easy, okay? So just think about it. You start off at the beginning of a reaction, and you've got all reactants and no products. But then as time goes on, the reactants concentration gets less and less because it's getting turned into products. And the products grow more and more. Do you see how this is the most unnecessary and easy graph ever? But they will put it on the test and say, which one, shows what happens, and that's the one. So easy. Okay, so a couple of things to notice about this is that the rates for this one are, in this graph, they're equal and opposite. And that means that the coefficients would be the same. If you had something where you had 1 for the coefficient of your reactant, say you've got a decomposition reaction, but you're making products that had a coefficient of 2, then these amounts, the concentrations, would be a little bit different. So that we'll see that maybe more in our I do, we do's. So that's the only thing that makes this all complicated, is sometimes they reflect the molarity. And then another thing that's just real obvious is it starts fast, but then it slows down, okay? So the reaction rate changes, okay? And then another thing about this graph and about this unit is, according to Jeremy Krug, all rates here are positive. I watched several videos of different people doing notes. Some people had some things as negative, but I feel like Jeremy Krug really understands what's on that AP test. He's been teaching AP chemistry for like 18 years, and he always says this is on the test and this is not. And he said all the rates are going to be positive. So we're going with Jeremy there. Okay, so the general formula for rate, like speed equals distance over time, right? But this isn't speed. This is change in concentration over change in time. It's just a regular rate, formula. And here's an example problem. If the initial concentration of A is 0.5, and after 10 seconds it drops to 0.35, what's the rate? So we just subtract to get the change. It's 0.5 minus 0.35 divided by 10. And you should get 0.15. Now I want y'all to get, and this would be our molarity divided by seconds. I want everybody to have your calculator out. We're going to be doing a lot of example problems. I want you to calculate along with me. Every problem, I want to make sure you can get the same answer I got. Okay? Anybody need to borrow a calculator to calculate along with me? If you do, bring these collateral and come get one right now. All right. Okay. Yes, sir?
The 0.15 per second, would that number is just without the division by 10 for the seconds? Because if it was divided by 10 per second, it'd be 0.015.
I left off at 0. Let me do it. I'll calculate along with me too. Let me double check that I put all my numbers in right.
I 0.35.
You're probably right. Yep, you're right. I see it. I left off at 0. Okay, look. We'll just put the point right there and a big old 0 right there. And then it's perfect. Okay, everybody, good thing. Okay, so this is the next part. So you can find out the instantaneous rate anywhere along that curve by doing a line tangent to the curve. Its slope is the instantaneous rate. Now this is kind of getting into some things you learn in calculus and things like that. I don't know how much this is on the AP test. So all I want you to know right now are these words that you can get the instantaneous rate by putting a tangent line to the curve. I just want you to know that definition. We will look and see if there's any problems with it, but I think there's not. So if there's, I'm trying real hard not to teach you things that are more than what's on the test. So right now we're going to not do any problems with this and just leave it here. Okay, until we look at the I do, we do's and some practice tests, I don't think we have to know more than that. Okay, next, introduction to rate law. So rate law provides a mathematical description, formula kind of thing, of how the changes in the amount, AMT is the chemistry abbreviation for amount, of a substance affect the rate of a chemical reaction. So changes in concentration, how does that affect the amount? And this is where we get to do a little math. Yay! Okay, so first of all, to do these problems, you have to look at some data. So there are different ways these problems are, but one of the problems is you'll get a data table. So here's a reaction, and these are we did three experiments, and these are the concentrations for our 3 experiments. Okay, now first we're going to review a little math, just to help you remember. I'm going to add 1. What does x to the 0 power equal? 1. Okay, remember that. So remember that anything raised to the first power is itself. Everybody remember that? And the second power means that it's times itself. And to the third power is times itself 3 times, right? Okay, so what we're going to do is we're going to look at this data and figure out what's happening mathematically. Now, a lot of you can do math really good in your head because that's what got you here, is you are good in science and math. And so when I show you this problem, you're like, yeah, you'll kind of like know the answer without realizing what you did. You're just going to look at it and know the answer. But I want to show you what you did in your head, whether you realize it or not, because on the test you might be panicking and you'll be like, I don't know, it might not pop into your head. Does that make sense to you? Okay, so what we're going to do first of all is we're going to look at where the concentration of the hydroxide stays the same, but the concentration of ClO2 changes. Okay, and so that's experiment 1 and 2. Everybody agree to that? Okay, and what we want to see is how does the concentration of ClO2 change mathematically in regard to how the rate changes. Okay, so first of all, we want to think about mathematically what is going on with the change here. How did we get from 0.02 to 0.06 mathematically? So what we did is what you are doing in your head, even though y'all probably already figured this out, is you're asking yourself, what do you multiply by 0.02 to get 0.06? And it's 3. Everybody agree to that? Okay. And over here, our rate, we're going from 0.00276 to 0.02480, and some of y'all can just sort of see it in your head, but if we're asking ourselves, what are we doing to multiply to get from this to this? We are solving for x, and it's 9. We would divide that into this, and you get 9. Okay, everybody understand so far what we've done? Okay, next, you look at these two numbers, and you're looking for an exponential relationship. What do you raise 3 to get 9? 2. So this is, the answer is 2, and we look at that and we say this is a second order reaction. And that would be the question. What order is this in respect to this chemical? And the answer is 2. Okay? Good so far? See, it's not hard, but it's a little fancy. Yes, ma'am?
Will the order reaction only go up to the third power?
Yes. And third is going to be rare. If things to be, because the more chemicals you have, that's more things that have to be oriented just right to react, and their chances go down. Okay. All right. So then now we're going to look at the OH. We want to see where the OH changes, but the Cl2 stays the same. So we're going to look at the Cl2 stays the same. That's 1 and 3. OH changes. Everybody see that? Okay. So now look here. Mathematically, we went from 0.3 to 0.9. So we multiplied 0.3 times 3. And then we went from 0.00276 to 0.00828. And if you do that, it solves to 3. We multiply by 3. So what do you raise 3 to get 3? 1. Remember, anything raised to 1 is itself. So this is a first order reaction. So they'll give you a little data table and ask you that question on the AP test. Can you do it? Yes, you can. Okay, so then they'll ask you the overall reaction, and you just add them up. So 2 plus 1 is, see, I told you it wasn't hard. It's just got to remember what to do next. Now, so then the other thing they'll ask you is what is the rate law? So this is an equation, and this is how you write it. This is a little like when I taught y'all honors of equilibrium. I'm not sure that Miss Korn did though. But either way, it's just you now fill it into this formula. You write rate equals K, just write the letter K. I'll explain to you where it comes from. Then write the concentration of your first reaction raised to its order. And our first one was second order. Then you write your second reactant as a concentration, and you put what order it is, but if it's a 1, you don't write it. Everybody see how I got it? Okay, now the next thing they'll ask you is what's the overall sometimes, and that's 3. So sometimes you can see 2. Sometimes they'll just give you this and say what order is it, and you just add them up. 2 plus 1 is 3. Tells you it wasn't hard. It's just fancy. Okay. Now, then they'll ask you what K is. So what you do is you pick any one of the 3 experiments and you fill it in. So I picked the first experiment and I filled in that for the concentration of Cl2. I filled in that for the concentration of OH. And I filled in that for the rate. Everybody see where I got my numbers from? Okay. And then I put them in this equation and I solve for K. So I want everybody to do that right now because we are computing along with Miss Blackburn. So everybody put in your calculator 0.00276 divided by 0.02 squared. And notice you have a squared button you can hit on your calculator. And then enter, and then 0.03 enter. See if you get it. Let me turn to the right page here. You should get 230. Y'all getting 230? I don't see any nods. Anybody get 230? Yes. All right. Woo! Got some nods. Okay, so one thing that's considered a tricky part of the AP test is when they ask you for the units of K. And the units of K are different if it is 0 order, first order, or second order. Third order doesn't really happen very much. Well, third does, beyond that doesn't. Okay, so some of the AP teachers I watched online said you need to memorize this. But there's a way to figure it out, and I always like figuring out better than memorizing, so I'm going to tell it to you. So how you do it is, the order for time always goes in the denominator. So seconds is always in the denominator, because if you remember our original rate equation is change in concentration over time. Okay, so everybody's got it, time's in the denominator, right? For the numerator, it changes depending on what it is, and this is how you do it. What you do, capital M, molarity, to 1 minus whatever order it is. So if it's a 0 order, 1 minus 0 is 1, m to the first power is just m, so the unit is m in the numerator, seconds in the denominator. Do you follow that? Okay, now, before I get to the next one, next one I can do. Okay, so first order, 1 minus 1 is 0, and anything to the 0 power is 1, and we don't write ones, right? Everybody remember that mathematically? So you just put 1 over s for the unit, or s to the negative 1 means 1 over s. Everybody get on that one? Now I want to teach you something. Now, some of you already know this, but according to first period, some of y'all don't. And that's negative exponents, okay? So in math class, when you have things to a negative exponent, this is how I teach it. Do y'all remember the video game Portal? It's kind of old, but have you ever played it? Okay, so if you haven't played it, you have this gun, and you can shoot holes in walls and go through them. You could go to the side, you could go to the ceiling, you could go down. And you shoot a hole and you drop through. That's Portal, fun game, puzzle game, okay? So what I say is these negative exponents are portal guns. But we only have one wall that we can go through. See the fraction bar? That's the only wall. So what the portal gun does is it shoots a hole in the fraction bar. Whoops, I got the wrong pin here. That one won't work. Shoots a hole in the fraction bar, making a portal that the X can go through. But unlike the game, the gun is lame and it can only shoot one time. But it takes the base and its exponent through to the other side. Oops, now we got a phone call. This is very high quality YouTube creation here. Hello. Oh. Yes. What day is it going to be? All right. Excellent. Thank you for letting me know. Bye. I got an inside scoop on when the Black History Month program is going to be. Because Miss Weeks knows I love to take my class. Okay. Anyway. Okay, so we shot through. So here's another one. He's going to shoot his portal, and he drops through. When he drops through, he loses the negative, but he keeps the exponent. So in algebra, that is that simplified. Everybody remember that from algebra? And it goes the other way. So if you have this, you get a portal, it pops up there, and this equals yx squared. Everybody remember that from algebra now? How to deal with negative exponents? I think it's a really fun thing. They put that question on the ACT and the SAT, and I'm like, ooh, the easy question. All you have to do is use your portal gun. Drop, 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 mark, mark, mark. Very fun little algebra problem. Okay, so here we've got this one. So now for second order, it's going to be 1 minus 2 is negative 1. So that means that this big M is dropping to the denominator. So for the second order, it's 1 over ms, or m to the negative 1, s to the negative 1, because negative 1 means it's dropping to the denominator. Everybody follow that? Okay. And then for the third, it's 1 minus 2 is negative 2, so it's m to the second power s in the denominator, or n negative 2 s negative 1. So now you don't have to memorize it. Just remember it's 1 minus the order. And now you can get that question right on the test. Maybe you should have a list of things to look over the night before. Maybe that's one of the things you should look over just to remind yourself, because it's not hard. Or you have to memorize them. Okay, section 3. Concentration changes over time. So the first question they'll ask you is they'll give you that data table and you got to figure it out. The other thing is they'll give you data and you graph it and you can figure it out that way. Or they'll give you graphs you look at and you'll know the answer. Let me explain. Okay, sometimes your data shows how the concentration changes over time and you can tell by graphs. And the question you ask yourself, is it a straight line? What are we looking for? Straight line. That's the right answer. So, which order of reaction? So, if it is 0 order, that means that the concentrations don't matter, that is the rate equals the constant. The graph of the concentration versus time is straight because anything raised to the 0 power is 1 mathematically. Okay, so now everybody scroll down, look at the graph. This is what the 0 order looks like. Do you see how concentration's over here? Time's over here? See how it's a straight line? Okay, if you see this graph with concentration over here, time over here, straight line, it is 0 order. This is a matching question. Okay, everybody good so far? Okay, let's look at the next one. If it is first order, then it is the graph of the natural log of the concentration versus time is straight. So, let me explain what this means to y'all, because first period didn't know about natural logs, so let me review logarithms for you. So I've got over here, but I'm going to write it over here because the people on YouTube even can't see it. Okay, so what logs are is log answers this question. So 2 to the, what do you raise 2 to, whoops, I can't write, to get 6, okay? We know 2 squared is 4 and 2 cubed is 8. Well, what would you raise 2 to get 6? So just like how adding is the opposite of subtracting, logs is the opposite of exponents, okay? Kind of thing. All right, so that is what the question is. So this 2 is called the base. So you do log base 2. Now, back in the day of the 80s, when I was your age, they would always use log base 10. 10 was the only base they would use. The reason why is these are complicated things. As you can tell, this is going to be some decimal, right? You see how that's some big old long decimal? So they would have them all in books. And I remember, that was before my time, the books were. But a long time ago, they used something called slide rulers. I don't know how to do it. It was in the 70s. And they would have these answers in books to these questions about logs. And I remember seeing them when I went to college. They were green books all along the side of the wall of my lab. And I never looked at one. I don't know how to use them at all. But people a little bit older than me do. So then they made calculators that could do log base 10. So on your calculator, there's a button that just says log, and that's base 10. And the reason why they did that is that way they could ask us test questions without us having to go look in the books. Okay. Well, then in the 90s, the TI-84 came out. And it could do different bases. So everybody who's got a TI-84, get it. And turn it on and go to the button that says math. Now, I call this the ironic button because aren't they all math? Yes, they are. Push the button that says math, scroll up to, up, and you will see log base. Do you see that? So that is a button where you can put any base problem and solve it by changing the base with this calculator. It's one of the reasons you want this calculator is that thing that I just showed you, okay? Now, there is another base you can have, and there's a thing called natural log. And instead of doing LOG, it's LN. Look on your calculator for the button that says LN. So what natural log is the base is not a whole number like 2 or 10. It's a number like pi. You know how pi is this number that's got a name, and it goes on forever without repeating, right? Well, there's another number just like pi, which is lowercase e. It's Euler's number, and it's equal to 2.1718 to infinity. Now, pi is very popular. People all know about pi, and they memorize it to like 20 places for no good reason. But everybody doesn't love Euler's number for some reason. It's just as great. Nobody bothers to memorize it to 20 places. And I think it might be because pi is something delicious you can eat, and Euler's number is not. But I don't know. But anyway, so Euler's number is the base. The symbol for Euler's number is this little e. Do you see a little e on your calculator? You found it? It's probably the second of the natural log button. So natural log, the base is e. And there is a lot of stuff we do in chemistry with this number. So we're going to be doing more with natural logs than you've probably done before. Do you understand what a natural log is now and kind of what we're doing? Okay, so back to this chemistry. If you graph the natural log of the concentration versus time, that makes a straight line if it's first order. So everybody scroll back down to or look over at the first order graph. Do you see how this is natural log of A versus time? So they would just give you concentrations. You take the natural log of a few of them, and I'll show you how to do that in just a second. And if it makes a straight line, or it's a matching question, you find the one where natural log of A is a straight line, it's first order. Okay? Not too hard, is it? Just kind of fancy. Okay, now what about if it is second order? This time the graph is 1 over the concentration. So look on your calculator. You have a button that is x to the -1, or you have a button that is actually the number 1/x. Everybody find it? That's the button we'll be using for that. This is the inverse. If it's second order and you graph the inverse of the concentration, then you get that straight line. Ta-da! Okay, how are we feeling about this brand new thing in our life? Good. Okay, so now sometimes they will give us numbers for us to do with this. So you don't have to memorize these equations. They're on your AP reference sheet under kinetics. So you just have to be able to use them. Know when to use them and use them. And it's just plug and chug. They will give you numbers. You put it in the formula. You get the answer. So easy. So let's practice some of those. So this is called integrated rate laws. These are formulas on your reference sheet, and we can figure out the concentration at any time using math. Okay, so here's our first order reaction. That is the way it is written on your AP sheet, and here is our example problem. If the rate constant, that's K, for a first order reaction, they would not give you the equation. You're going to have to go first order, go find it on the equation to use it. Okay? Everybody understand that? Okay. So that's the rate constant, 0.05. The initial the initial concentration is 1. So do you see how it's A sub 0? That's your first concentration. That's when time is 0. Put it in right there. How long will it take for the concentration to decrease to 0.25? That's your concentration that goes right here. So I substituted it in. I want everybody to try it on their calculator right now. Natural log, hit that button. 0.25, put it in the parentheses. Minus, use minus, do not use negative or you will get the wrong answer. Natural log of 1, in parentheses, equals, then do divided by negative, not minus, 0.05, and see what you get. Everybody do it. I'll tell you the answer. I think I memorized it. Yep. Yeah, it's 27.7. If you didn't get 27.7, do it again. And if you still didn't get it, show me and I'll look at your calculator and see if I can help you. Are y'all getting it? Was it fun using a new button on your calculator and understanding what it means? Yes, it was fun. Math is great. Feel smart. Got to do some natural logs today and even knew what that meant. Okay, so here's a second order problem where you're going to get to use your inverse button. That's fun. So this one is second order. If a reaction is second order with a rate constant of 0.15, that's our K. An initial concentration of 0.3, that's our A sub 0. How long will it take the concentration to decrease to 0.15? So here I've substituted it in for you. 1 over 0.15 minus 1 over 0.3 divided by 0.15. Everybody try it and see if you can get, I think it's 22. Let's see what the answer is. 22.22. I want you to try to use that inverse button on your calculator. Don't do 1 divided by parentheses, all that. Let's try to do it the fast way. Use that inverse button. Are y'all getting the right answer? 22.22. Or something about that. Somewhere around 22 you should get for your answer. Yay, I see nods. Yay. Very good. Math is a fun game that you can win because the best jobs that correlate to the best majors use math. It's engineering, it's accounting, and it's science. So math is a fun game where you can win real money by being good at math one day. Okay, our third equation that is in the kinetics part of on your AP reference sheet. This is the only 3 equations, is one for half-life. So we can use these ideas of kinetics to actually solve for half-life. Remember how we learned in honors about isotopes that are unstable and they fall apart and become something else. And the time it takes for half of them to do that is called the half-life. Everybody remember that from honors? Okay. So also, so there is some math we could do. Now, we have learned since my day in the 80s. In the 80s, we thought half-life was as constant as the rising and the setting of the sun. And we made atomic clocks, and we thought nothing changed, and it was perfect. But as time has gone on, we have found out that half-life maybe isn't as great as we thought it was. But in AP Chem and in high school Chem, we pretend like it is constant as the rising and the setting of the sun. Okay, just know that I know that new data shows that maybe half-life isn't as steady as we thought it was. Half-life makes assumptions, and whenever you make assumptions, you're opening yourself up for error in science, right? And it's making assumptions about the past, and we don't have a time machine, so we can't, get rid of all the assumptions. Okay, so this is the formula. It's just like that on your AP reference sheet, and here's a problem. A radioactive isotope decays at a rate constant, so that's our K. What is the half-life? All you do is do 0.693 divided by the number they give you. Everybody give it a try and see if you get the answer. It should be 300 seconds. Everybody try it on your calculator. See, this is fun, isn't it? You're learning something new. It's not boring. Don't answer that. I don't think so. I think it's fun. I like it. This is the kind of stuff I like. I like math that's a little bit fancy. And something new and different. Okay, everybody got 300? Yay. All right, next idea. You learned in honors that sometime when you learned Hess's law, you learned that sometimes reactions happen in steps. Does everybody remember that from honors? If not, reactions can happen in steps. Each step is called an elementary step. You add them together, you mark out things that are on both sides of the arrows, and you can get the overall reaction. So on this one, draw a little plus, and let's look at what we can mark out. Well, if you look, there's an NO3 on the reactants, and there's an NO3 on the products, so we can mark those out, okay? There's an NO2 on the reactants and an NO2 on the products, and we can mark those out. And then we add them up and we get the overall reaction. Everybody like that? I think that's kind of fun. I like marking out in math and science. It makes me feel powerful. You're not the boss of me problem. I'm the boss of you. I'm going to mark things out. I don't know why. I've just enjoyed it. Ever since I was very young doing math, I've enjoyed canceling out. It's been the fun part. Okay, so the next idea is the steps. There'll be a slow step and a fast step. And the one that controls the rate of the reaction is the slow step. Okay, so that makes sense, right? Okay, so now this is what the graph looks like. We have done reaction graphs before, but now we got two hills, two steps. Things that are formed and then go away. So look at this. Do you see how NO3 was made and then in step 1? And then it was used up in step 2 and it went away and is not in the overall equation. Can everybody see that here? That it has a special name. It's called an intermediate. It is a stable little thing that lasts for a little bit and then it goes away. Okay, so there's our intermediate. It's stable. Now the what you have at the top of the hills is not stable. This is where bonds are broken and bonds are formed, and they're not stable. But the little intermediate in between in the valley is stable. Okay, each step has its own rate, and the only one that matters is the slow step, and it's also called rate determining. The only step that matters for the speed is the slow step. It's the one that's going to control. Okay, so here is the rate is the reaction A times reaction B times however many you got. So if you look back at our formula, look up here. The only one that matters is the slow step. So if I'm writing the rate formula, I don't look at the overall. I don't look at the fast step. I only look at the slow step. So for my slow step, you only look at the reactants, not the products. And my reactants are NO2. So my rate is the concentration is K times the NO2, but I have 2 of them. That's the rate for that reaction. How do we feel about that? You find the slow one and just write it for it. And we had 2 of those, so we put a 2. So it's overall, it's second order because of that 2. With respect to NO2. Now sometimes if you only have one molecule, it's going to be first order. If it's bimolecular, it has 2 molecules, so it's second order. We had 2 molecules because of that 2. It was bimolecular and it was second order. So that's just vocabulary. Everybody understand that okay? Okay, next idea, collision model. And this comes out honors. Collision theory states that for a chemical reaction to occur, the reactant particles must collide with enough energy and in the right orientation. The rate of the reaction depends on the frequency of the collisions. The theory also tells us that reacting particles often collide without reacting. When they first collide, it is a mishmash called the activated complex. I made that up, calling it a mishmash. But they're just like things are breaking, things are being formed, nothing's stable. And that's the top of the hill. That's the activated complex. It's also called transition state. It's unstable and only lasts a few seconds. So that's the activated complex. Bonds are broken, bonds are formed, and then it goes on to the products. Okay? This graph shows how increasing the temperature increases the collision and more get past the energy of activation. So this is the graph it's talking about. So this is where it gets to actually react. Notice that down here at temperature 1, nothing gets to react. Nothing makes it to the energy of activation. Temperature 2, a little bit makes it pass. Temperature 3, but the one that has the most reacting, the fastest one is temperature 4. Why? Because more of it is past the line for energy of activation. Do you see how they can ask you multiple choice questions on that graph right there? Basically, do you understand it? more of the purple gets under. And I know y'all's graph doesn't look as good, but you can kind of see it. Not temperatures where not many pass the line are slow. So they could ask you which one's fastest. T4 is fastest. Okay, so here you learned this in honors. We have some reaction energy profiles. Exothermic, the reactants are higher than the products. Endothermic, the products are higher than the reactants. Do y'all remember that from honors? Everybody remember those reaction diagrams? I think that was unit 8 in honors. If you add a catalyst, it will lower the energy of activation. See the green line? That's adding a catalyst. All right, unit 5.7. We good? Am I going too fast? Okay. So 5.7, once I started looking at it, I realized I already taught it in 5.4. I got ahead of myself and I didn't try to go back and break it down. I'm like, I'll just tell them, you already know this. Okay, 5.8. Wasn't that one painless? Okay. So there's reaction mechanisms and rate law. Here's my little key. I proclaim a law. So this is a two-step reaction, NO plus Cl2. Okay. And it's got 2 steps. Everybody take a look at it. This is our fast step. That's the slow step. Step 1, we made this intermediary. And then step 2, we used it up. Which step matters for the rate? The fast one or the slow one? The slow one. No, so we only write the rate from the slow one. But the slow one has an intermediary, and that's not allowed. We can't write a reaction expression for this using something that's not even in the reaction. Does that make sense to you? Not allowed. So what we do instead is we go back to the fast step and we see what chemicals made that up. Well, it was the NO and the Cl2. So instead of writing NoCl2, we're going to substitute NO and Cl2 for NoCl2. This reminds me of something that I would do in geometry. Remember the geometry rules? When you would do line segments and you would put them in, or angles, remember that? It's just like that. Instead of writing that in our rate, we're going to write those 2 things. So this is our overall equation. This is what you would think the rate is. Nope, not allowed. So we're going to take that's not allowed, and instead we're going to put in what makes it up. Okay, but then we gathered up our NOs and squared them. So that is how you would write that one. How do we feel about that? Not hard. Just got to remember to do it. And because that other one's going to be a wrong answer for you to choose. They're going to be tricky. They're putting that one on there. But you got to find the right one for your multiple choice. Now, what we just did, section 5.9, is called steady state approximation. We could call it substituting in when you have an intermediary that's not allowed, and that would make sense. But we're nerds, and we like fancy names for things in science. So substituting in for an intermediary that's not allowed is called steady state approximation. That's all there is to that unit. Look how great this is. All right, now we're on section learning target 10. The multi-step reaction profile. We have learned about reaction profiles, and they've always had one hump. But now we've learned that reactions can take place in steps, so for each step, it's got its own hump. Now, so this is the first react part, that's the second one. There's our intermediary in the valley. Which one do you think is the slow step? 1 or 2? Which one do you think in this little graph is the slow step? They're going to ask you that. Which one do you think is the slow one? Just by logic. He's got it. It's 2. Why is 2 the slow one? Because it's a bigger mountain and that'd be harder to get over, right? If you were a little hiker, this one would take longer to get over, right? Now on the AP test, you can't say it's got a bigger mountain. So the answer is, which one? That one. And the reason why that we're going to say on the AP test is that it has a bigger Energy of activation. Oh, doesn't that sound better than a bigger mountain to climb over, right? It's got a bigger energy of activation. Okay, last section. Oh, we have gone so fast. Okay, maybe I've gone too fast. Maybe not. Okay, sometimes reaction need a catalyst. And that's like a little push over that hill to get them over that hill. So our last section is about catalysts. Some of this is from honors. Okay, so a catalyst is sometimes like a matchmaker. They'll go get one chemical and another one and hold them together for them to react. That's what enzymes do in your body. They'll actually go get them. Sometimes it's different, but sometimes it can put chemicals together so they can react. An example is enzymes in your body that are made out of proteins. Gotta eat your protein. They're made out of proteins. Okay. Catalysts speed up a reaction without being consumed in a reaction. What that means is you put them in at the beginning, you get them out at the end, and they make it go faster. Okay, so here is an example. Here we have a two-step reaction, and it's got a catalyst. Everybody look at that and see if you can figure out what did you put in at the beginning, get out at the end, and it's not in the overall reaction. Can anybody find the catalyst? This will be another AP Chem question. What's the catalyst? What is it then, Sheila? PT is the platinum. Platinum is often a catalyst. It's real common. So does everybody see how Sheila did that? Do you see how PT's at the beginning and PT's at the end, but they mark out and they are not in the overall equation? That is the catalyst. Now, do you see the intermediate? What is something that is made in step 1, used up in step 2, and not in the overall equation? Can you find the intermediate? What is it? H2O2 made it to the overall, so it's not that one. Find something that's not in the overall. It's made in step 1 and used up in step 2. PTO. Look right here. We made some PTO. It made it down to step 2 to get used, but it didn't make it to the products. So that is our intermediate, our PTO. Can everybody see that that's the PTO? Yeah, see, I told you this wasn't hard. It's not hard, is it? Nothing I've showed you is hard. The hardest thing is like natural logs, but you don't have to use the slide rule. You just put it in your calculator. Okay, so sometimes you're given reactions like this, and you're asked to guess the fast or slow step. So here we got 2 steps, just eyeballing it. Which one do you think would be harder? Thinking about collision theory, which one do you think might be the slow step? Step 1, A plus B makes AB, or step 2, AB plus B plus C equals ABC plus B? You he said step 2. You are correct. Can you tell me why? Instinctively you know. Why do you think it is?
It just looks like it needs more energy.
It looks like it needs more. It's because this is bimolecular, this is termolecular, and so you've got more chemicals that need to collide with the right energy and the right orientation. So our odds go down for a successful smack. They got to smack together at the right orientation and the right energy. That's going to be a little harder to do. Does that make sense to you? Okay. So is it more to hit just right? So we were correct. Okay, next, here's another one. Sometimes you're given 2 reactions and asked which is faster. So here we have 2 reactions. Can anybody have a guess what is different about these 2? They're both bimolecular. Which step do you think is going to be faster of these 2, 1 or 2? Can you figure it out? And let me just say here, there will be questions on the AP test you do not know. They just make it that way. It's how they make the SAT. It's how they make the American Chemical Society exams that you're going to have to take in college. And there's just going to be questions you don't know, and you are going to have to kind of figure it out with your prior knowledge and your smarts and your gut and taking a well-educated guess. Yes, Aunt Shula?
I think 2 because it has a lower rate constant.
Okay, so let's look at these. What they're doing here is they're trying to be tricky by writing these in scientific notation. That is, they're trying, remember, this isn't a regular test. This is a tricky test, and you're trying to figure it out. So I'm going to take these out of scientific notation. So this one is 0.03, and this one is 0.0004. Which number is bigger? That one, right? Do you think bigger is going to go faster or slower? It's bigger goes faster. So the answer is reaction 1 because K is, we won't say bigger, that's not real sciencey. We'll say K is greater. That's more sciencey, right? Oops. Now Ruben's freaking out a little bit. So it's the one with the bigger, I'm going to say bigger here. The one with the bigger rate constant is going to go faster. So it was reaction 1. All right, that's it. That's kinetics. Yay! Science is great.